I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video. I am demonstrating and showing you a very important chemistry concept that the K is dependent on T. What is it? Equilibrium constant for a chemical reaction is always dependent on the temperature under which that reaction occurs. We will demonstrate that to you mathematically and we will show you example here in this video. Everything starts with this famous equation, delta G is equal to delta H minus T delta S. You know this, gives free energy. The change in free energy is equal to the change in enthalpy minus temperature times the change in entropy. This equation is not the focus of our video, but it can be a focus of another video, but this comes into play for what I'm showing you for the video. Our main equation is what ties in your equilibrium constant with this expression over here, and you may remember and know this equation from your own studies. K is equal to E to the power of minus delta G over RT. This right here is the equation which will demonstrate everything for you in this video. K, your equilibrium constant, is equal to E to the power of minus delta G over RT. Now what do I know delta G to be equal to right here? Delta G I know is equal to this. So we modify the equation to this. K is equal to E to the power of minus delta H minus T delta S. You want to parenthesize this because the minus is impacting everything right over here, divided by RT. What we do here is modify this using laws of exponents. Prior to that, distribute this minus across. I have E to the power of T delta S minus delta H. You see the minus impacts everything in the parentheses and it flips things around, divided by RT. Modified some more is equal to E exponent. I'll have T delta S divided by RT times E to the power of minus delta H over RT. What have I done? I've separated this first across the minus, then into individual exponents. Why? Because A to the power of M times A to the power of N is equal to and interchangeable with A to the power of M plus N. That's exactly what we have over here. It's a law of exponent coming into play. Now that we've done this change and manipulation, you can see your K value, your equilibrium constant, is equal to this right here, E to the power of T delta S over RT times E to the minus delta H over RT. You can even further simplify it. The T's cancel out. You can say here at the end, K is equal to E exponent delta S over R times E to the power of minus delta H over RT. A very important concept comes out from this manipulation, one of which is this. You see, when you look here in the Gibbs free energy, delta G is equal to delta H minus T delta S. When you focus only on this part right here, I have E to the power of delta S over R. You know R is your universal constant, 8.314, and you know the units. Joules over K, Kelvin, mole, temperature mole. Anyhow, we won't digress too much. We know R is equal to 8.314, but I'm looking over here. When I'm looking at this, I have E exponent delta S, your entropy divided by your constant. It's showing you the temperature has been lost. So entropy, the concept or the act of entropy, is not dependent on temperature unless you're worrying about temperatures at the very extremes, where you would know the Kelvin temperature to be 0, where the motion of molecules will stop, or at extremely high temperatures. But at the normal temperatures where we will conduct our chemical reactions, and at the varieties of other temperatures, entropy is independent of temperature. What is dependent on temperature is this enthalpy delta H. As you can see, the temperature factor retains. So let's bring everything here into unifying front over here, then we'll talk about how K is dependent on T. So this is where we are now. The equilibrium constant is equal to E to the power of delta S over R entropy divided by R times E to the power of minus delta H, your enthalpy factor, divided by R and T, temperature. What you can say is, since I've told you entropy is independent of temperature and it's not affected by temperature for the normal range and for the areas outside of that normal range, unless we are worrying about extremes, and we are not, it is independent of temperature. So you can generally say, for the purposes of this demonstration where K is dependent on T, we can just say this is equal to E to the power of minus delta H over RT. I'm not saying it is equal to, but I'm saying we can eliminate it for the purposes of this video. When you focus over here and you remember the R, the constant that you have over here, what we do is demonstrate for you this effect, and we will do so by means of a table. Imagine you have two reactions. One reaction will be A plus B to give you C, and you have heat coming into play, it's going to be endothermic. Then you have another one, A plus B is giving you C plus heat. This will be exothermic. We will examine these individually and we'll show you the equilibrium constant is indeed dependent on temperature. This will be our example, let's say 1, and this here will be example number 2. Let's look here at this and we'll do a table for you. What I will show you here now by means of this table, how the K is dependent on temperature, a fact that you learned very early on in chemistry, the Le Chatelier's principle, where the temperature for an exothermic and endothermic reaction plays into this value right over here. And yeah, we're looking here at equation number A plus B in an endothermic reaction where heat is involved gives rise to a product C, and this is the information we're using with regards to this formula we have. And for an endothermic reaction, I have an enthalpy of 1000, temperature changes from 273 to 400 Kelvin. How does the K respond? So we are looking here at this formula. Let's plug in these items right here into that formula and see what happens with the K. I have a minus delta H, which is a 1000 and a minus divided by 8.314, my constant, divided by temperature 273 Kelvin. And I'm going to invoke the exponential base. I have 0.643. That's my value for K. K has no units. And now let's look here at this next set of data and see what happens. The equation formula is still the same. I have a 1000, which is a minus divided by 8.314 divided by my new temperature. The temperature has risen up 400. I'm going to invoke the exponential base. I have a 0.74. So what happens? We see a clear trend. Something happens over here, and what is that? You will see that for an endothermic reaction, as the temperature goes up, the K value, the equilibrium constant, must also go up, and that's a fact that you should remember. For an endothermic reaction, as the temperature is increased, the equilibrium constant is increased. And you can remember this because it is one of those factors that play into the value of this. Let's look at everything now for an exothermic reaction and see how everything plays out. Now for an exothermic reaction, as you see right here in number 2, A plus B giving rise to C plus heat is released, the enthalpy values must be minus, because that represents an exothermic reaction. The temperature still increased. Let's see how the K value responds. Everything is coming here into this equation, but except you'll notice this minus and these minuses will cancel out. So this minus 1000 will become a positive 1000. I have 1000 divided by 8.314 divided by 273. I'm going to shift the exponential base and activate it. I have a 1.5536. That right here is my value, 1.5336. I have rounded up to 1.54. Let's see what happens when the temperature is increased for an exothermic reaction. Minus 1000 becoming positive by means of that. I have a 1000 divided by 8.314 divided by 400. I'll invoke the exponential base. I have 1.35. Now I'm seeing a clear opposite trend. What is that trend? For an exothermic reaction, as the temperature goes up, the equilibrium constant value must come down, and you're seeing that it's an exact opposite trend. For an endothermic reaction, as the temperatures increase, the K increases, but for an exothermic reaction, as the temperature is increased, the K value must decrease, because everything factors in by means of this equation over here, and you saw how it derived from the Gibbs free energy equation. By factoring in the Gibbs free energy equation into this one, which was K was equal to e to the power of minus delta G divided by RT, we substituted everything right here in the delta G, the Gibbs free energy part, into that, and it demonstrated everything that you saw afterwards. So we end this video with these two concluding statements. The opposite of these statements will also be true. The equilibrium constant of an endothermic reaction increases as the temperature increases or is raised. Therefore, you can assume the equilibrium constant of an endothermic reaction will decrease if the temperature is decreased. Now consider this, the equilibrium constant of an exothermic reaction, where delta H is negative, decreases as the temperature is raised. Therefore, you can also assume the equilibrium constant of an exothermic reaction will increase as the temperature is decreased. So keep in mind the 4 scenarios. Only 2 are the official scenarios, but their affiliated statements also are true. So keep all of this in mind. Thank you for watching. Have a good day.